My name is Sheikh Afin Sultana. Today my topic is flip-flops from sequential logic circuits. First we see the definition of a flip-flop. A flip-flop is a bistable multivibrator, meaning it has two stable states. It can store binary information and maintain its state until it is changed by an input signal like a clock or control plus. Main functions of a flip-flop is store a single bit of data, change state only when triggered by an input signal. Remember its previous state, unlike combinational state circuits. Type of flip-flops. There are four types of flip-flops. First one, SR flip-flop, set or reset flip-flop. It sets or resets the output. Second one, D flip-flop. It transfers input data to output on a clock edge. Third one, JK flip-flop, an improved SR flip-flop. Fourth one, TK flip-flop, toggles the output state on each clock pulse. Here we see the clear explanation of this flip-flops. First one, RS flip-flop. An RS flip-flop also an SR flip-flop, and it is also called as set or reset flip-flop, is the simplest type of flip-flop. It is a bistable circuit that has two stable states, one representing logic 1 set and the other logic 0 reset. It is mainly used to store one bit of information. The logic diagram of the RS flip-flop is shown below, and these flip-flop will be implemented by using two NAND gates and two OR gates. Here we take inputs R and S and output Q and Q bar. The clock pulse is applied to the two inputs R and S NAND gates. And here we see characteristics table. First we can take in as Qn present state and input SR and next state Qn plus 1. If we apply Qn equals to 0, S equals to 0, R equals to 0, the next state will be 0. That state is called hold state. Here also Qn equals to 1 and S equals to R equals to 0, we can produce next state as 1, that is also called as hold state. This 0 1 is called as hold states. Here Qn equals to 0, S equals to 0, R equals to 1, the state becomes 0, and Qn equals to 1, S equals to 0 and R equals to 1, the state becomes 0. These two states are called reset states. Here Qn equals to 0, S equals to 1, R equals to 0, Qn plus 1 equals to 1, Qn equals to 1, S equals to 1, R equals to 0, Qn plus 1 equals to 1. These two states are called set states. Qn equals to 0, S equals to 1, R equals to 1. The state becomes 0 or 1. Here Qn equals to S equals to R equals to 1. The state becomes 0 or 1. These states are called invalid states. And we see the excitation table. Here Qn is the present state and Qn plus 1 is next state, and inputs are S, SR. Here we take a present state as 0 and next state 0. The inputs are 0 and invalid. Q1, that means present state equals to 0, next state equals to 1. The inputs are 1, 0. Present state equals to 1, next state equal to 0. The inputs SR becomes 0, 1. Qn equals to 1, Q1 plus 1 equals to 1. Here the inputs are S equals to invalid and R becomes 0. And this is about the RS flip-flop or SR flip-flop. And we can see this explanation of the working of the flip-flop. First one, set condition. S equals to 1, R equal to 0. The output Q equals to 1 and Q bar equals to 0. The flip-flop is said to be set condition. Reset condition. S equals to 0, R equals to 1. The output Q equals to 0 and Q bar equals to 1. The flip-flop is reset. No change. S equals to 0, R equals to 0. The previous state is retained. It remembers the last value. Invalid condition. S equals to 1, R equals to 1. Both outputs become 0, which is not valid since Q and Q bar must always be opposite to 1. And second one, D flip-flop, data or delay flip-flop. A D flip-flop is a type of flip-flop that stores one bit of data. It is called the data or delay flip-flop because the output follows or delays the input by one clock pulse. It removes the invalid state that occurs in an RS flip-flop. The circuit diagram is given below. Here input is D and D bar, and outputs are Q and Q bar. Here we see characteristics table. Qn equals to present state, D equals to input, and the next step will be Qn plus 1. Here we apply Qn equals to 0, D equals to 0, Qn plus 1 equals to 0, Qn equals to 0, D equals to 1, Qn plus 1 equals to 1, Qn equals to 1, D equals to 0, Qn plus 1 equals to 0, Qn equals to 1, D equals to 1, Qn plus 1 equals to 1. Here Qn is the present state, Qn plus 1 is next state, D equals to input. Here Qn equals to 0, Qn plus 1 equals to 0, D equals to 0, Qn equals to 0, Qn plus 1 equals to 1, D equals to 1, Q1 equals to 1, Qn plus 1 equals to 0, D equals to 0, Qn equals to 1, Qn plus 1 equals to 1, D equals to 1. This is the excitation of the D flip-flop, and the working principle is when the clock pulse arrives, the value at D is copied to Q. If D equals to 1, output Q equals to 1. If D equals to 0, output Q equals to 0. When there is no clock pulse, the output remains unchanged. Even if D changes, this ensures synchronized data storage with the input signal. And third flip-flop is JK flip-flop. JK flip-flop version of the SR flip-flop. It eliminated the invalid forbidden state that occurs when S equals to 0, S equals to R equals to 1 in the SR flip-flop. It is a bistable circuit that can store 1 bit of data, and it can change its output when both inputs are high clock pulse. Circuit diagram as shown below. Here we take inputs as J and K and outputs are Q and Q bar. And we see the characteristics table. Qn is the present state, J and K are inputs, Qn plus 1 is next state. Here we apply Qn equals to J equals to K equals to 0, the Qn becomes 0, and Qn equals to J equals to 0 and K equals to 1, the Qn becomes 0. And here we apply Qn equals to 0, J equals to 1, K equals to 0, Qn plus 1 1, and Qn equals to 0. Inputs both are 1, then next step will be 1. Here present state 1, next inputs are 0 taken as 0 zeros, and next step will be 1. Here present state, that means Qn equals to 1, the inputs J equals to 0, K equals to 1, the Qn n plus 1 equals to 0. Qn equals to J equals to 1, K equals to 0, Qn plus 1, Qn equals to J equals to K equals to 1, the present next state will be 0. Excitation table of this JK flip-flop. Qn is the present state, Qn plus 1 next state, inputs are JK. If in present and the next state are 0, the inputs are 0 and invalid. Present state equals to 0, next state equals to 1, J equals to 1, K equal to invalid. Qn equals to 1, Qn plus 1 equals to 0, J equals to invalid, K equals to 1. Qn equals to 1, Qn plus 1 equals to 1, J equals to invalid, and K equals to 0. The working principle of the JK flip-flop are when J equals to 0 and K equals to 0, no change. The flip-flop remembers its previous state. When J equals to 0 and K equals to 1, the flip-flop is reset, output Q becomes 0. When J equals to 1 and K equals to 0, the flip-flop is set, output Q becomes 1. When J equals to 1 and K equals to 1, the flip-flop toggles, meaning Q changes from 1 to 0 or 0 to 1. This is about JK flip-flop, and we see last flip-flop, that is T flip-flop, toggle flip-flop. A T flip-flop is a bistable device. It has two stable states that toggles its output on every clock pulse. When the T input is high 1, it is mainly used in counters and frequency dividers. The name T stands for toggle. The logic diagram of the T is shown below. T is the input and the Q and Q bar are the outputs. Here we see the characteristics table. Qn is the present state, T is input, Qn plus 1 is next state. Qn equals to 0, T equals to 0, Qn plus 1 equals to 0, Qn equals to 0, T equals to 1, Qn plus 1 equals to 1, Qn equals to 1, T equals to 0, Qn plus 1 equals to 1, Qn and T is also 1, 1, 1, then Qn plus 1 equals to 0. Excitation table of the T flip-flop is Qn is the present state, Qn plus 1 is the next state, T is the input. If Qn and Qn plus 1 is zeros, then the t becomes 0. Qn equals to 0, Qn plus 1 equals to 1, the t becomes 1. Qn equals to 1, Qn plus 1 equals to 0, the t becomes 1. Qn equals to 1, Qn plus 1 equals to 1, the t becomes 0. And working principle is when t equals to 0, the flip-flop does not change state. It remembers its previous state. When t equals to 1, the flip-flop toggles changes state on every clock pulse. If q was 0, it becomes 1. If q was 1, it becomes 0. This is about t flip-flops. And application of the flip-flops are first one, memory storage. Flip-flops store one bit of information 0 or 1. Second one, counters. They are used to count numbers or events like clock pulses. Third one, timers and clocks used in digital clocks and timers to keep track of time. Fourth one, data transfer. Flip-flops help move data from one place to another in a circuit. Fifth one, frequency divider. They can reduce the speed frequency of a signal. And this is about the application of the flip-flops. And we see the four types of flip-flops. We know that first one SR flip-flop, second one D flip-flop, third one JK flip-flop, and fourth one toggle flip-flop. And we see these four circuit diagrams as well as characteristics table as well as excitation tables, and we can also see the application of the flip-flops. And my talk and this is about the flip-flops. Thank you.